Hello everyone, welcome back to our AI series. In the last episode, we discussed search strategies in general. Today, we're going one step ahead into something more powerful: informed search strategies. Now, what do we mean by informed? Well, unlike uninformed search, which blindly explores the search space, informed search uses extra knowledge about the problem. This extra knowledge usually comes in the form of heuristics. Don't worry, we'll break this down step by step. Think of informed search as a smarter way of exploring possibilities. Instead of blindly going everywhere, it asks, which direction looks promising? Formally, it uses an evaluation function fn to decide which node to expand. Most often, fn is made up of two parts: gn, the cost so far to reach the node; hin, the estimated cost from this node to the goal. This is the heuristic. Together, fn = gn plus hn. If hn = 0, the algorithm reduces to uniform cost search. But when we add a smart heuristic, the algorithm becomes much more efficient. Let's look at the first informed strategy: greedy best first search. This algorithm says, always expand the node that looks closest to the goal, based only on hn. So here, fn = hn. For example, in the famous Romania map problem, if our goal is to go from Arad to Bucharest, we use the straight line distance heuristic. From Arad, Sibiu looks closest to Bucharest, so the algorithm expands Sibiu first, then Făgăraș, and then Bucharest. Greedy search often finds a solution quickly, but there's a catch: it's not always optimal. In fact, in this case, the path via Sibiu and Făgăraș is longer than the actual shortest path. That's why it's called greedy. It just grabs the nearest looking option without thinking ahead. Another drawback: greedy search can get stuck in loops or dead ends. For example, trying to go from Iasi to Făgăraș using this method can fail completely. Now let's talk about the most famous informed search strategy: a star or A. A combines the best of both worlds. It considers the path cost so far, GEN. It also considers the estimated future cost, ENN. So, fn = gn plus hn. This way, A balances between cheap paths already explored and promising directions toward the goal. What makes it really powerful is that, if the heuristic hn is well designed, A is both complete and optimal. That means it will always find a solution if one exists, and it will always find the best solution. But wait, for A to guarantee optimality, the heuristic must satisfy certain conditions. Admissibility: the heuristic must never overestimate the true cost. For example, straight line distance is admissible because the real road distance can never be shorter than a straight line. Consistency, monotonicity: this condition is stricter. It says the heuristic should obey the triangle inequality. In simpler terms, moving one step and then estimating the rest should not make things look cheaper than estimating directly. If a heuristic is consistent, a graph search becomes not just optimal, but also very efficient. A also has the nice property of pruning. That means it ignores large parts of the search space that cannot possibly contain a better solution. Imagine drawing concentric circles around the start node, where each circle represents states with increasing f-cost. A expands nodes in order of these bands, focusing only where the optimal solution can lie. This pruning makes A optimally efficient. No other algorithm can guarantee expanding fewer nodes and still be optimal. Sounds perfect, right? But there's a catch. A uses a lot of memory. In fact, memory often runs out before time does. That's why researchers developed memory-bounded search algorithms. One such method is IDA, or iterative deepening A. Instead of cutting off by depth, it cuts off by f-cost and gradually increases the limit. This reduces memory requirements significantly. Another is RBFS, recursive best first search. It behaves like depth first search but keeps track of the best alternative path. If the current path becomes too expensive, it backtracks intelligently. These memory-bounded versions trade off some efficiency for feasibility on big problems. So to sum up, informed search uses heuristics to guide the search. Greedy best first is fast but not optimal. A combines path cost and heuristics, giving us completeness, optimality, and efficiency, as long as heuristics are admissible and consistent. And when memory becomes an issue, we turn to IDA or RBFS. In the next episode, we'll look deeper into specific heuristics and see how they can make search strategies even more powerful. Thank you for watching. If you found this helpful, hit like, share with friends, and don't forget to subscribe for more AI lessons.